So today we're going to talk about graph neural networks for power systems. To be completely honest, I will have some slides before that, a bit more about, or more general about the applications of AI in power systems and some ideas. And then I'm going to talk a little bit about physics-informed neural networks, and then I'm going to talk about physics-informed graph neural networks. Okay, that's how I'm going to do that. And I have 45 minutes. And you're welcome to interrupt me whenever you'd like to. Okay, so let's start. Yeah. First, some acknowledgements. Really, I mean, this work that I'm going to present, of course, is not every person here has been part of the work I will present, but without this contribution or their contribution, I couldn't have been here. So many thanks to everybody. And many thanks also to our funding agencies, so the European Commission, also the European Research Council, because what I'm going to talk about today is actually funded by the ERC. Is this not working? Yeah. So what I'm going to talk about is a little bit about Trustworthy AI, or some thoughts about it. And then about, as I said, physics-informed neural networks, just a couple of slides, and then I'm going to focus on this graph and neural networks. So I don't know if you've realized or if you have thought about it, but AI and energy at the moment are two of the sectors that have been identified with the highest growth potential. Okay. So working, as I think most of you do, at the intersection of these two, is something that you will see a lot of development and interest in the coming years. Okay. For some reason, this is not. Just give me a moment to change clickers. Great. So, I mean, Mariam already presented a different application of AI. There are a lot of speakers that present application of AI. There are already applications, or let's say tools, AI tools that offer value to power systems and power system operation. Okay. And this started already from the 90s. We had the short-term load forecasting from EPRI that was actually adopted by several utilities. We had also the work of Louis Wenkel with decision trees for power system security assessment. This also found applications in utilities. So these were the first efforts, and 30 years later, to be honest, there is not too much, but there is quite some, especially over the last years. As you can see, it's a lot about forecasting, so also weather forecasting, predictive maintenance, energy trading. And now we're moving into new types of AI tools, right? So we have ChatGPT, we have generative AI. We have actually tools that we don't even know what they can do for us. And that's an open research topic. So far, we have seen real applications of generative AI into actually reading large documents like manuals, and then utilities send their technicians out in the field, and they no longer need to have, let's say, to know the manual, right? They get a step-by-step instruction on how to maintain or how to fix a component that is that's faulty. At the same time, this, to be honest, becomes a bit scary, and that's why I have this screenshot. It's actually from X or Twitter. So there is this question that some Alpan got from somebody: how much OpenAI, how much money have they spent on electricity just for replying thanks and please, right? And then some Alpan replies that millions of dollars, but it's well spent because you never know. It's a joke, but is it? Yes. So, would you be able to trust AI to run your electricity network? When millions actually, first of all, if something goes wrong, lives can be at risk. We had now the blackout in Spain and Portugal, and we're talking about some lives were lost and also millions of euros of economic damage, right? So you will not trust or you will not let something run your system or even parts of your system without knowing that it will not lead to such an unacceptable behavior, right? So what we need is trustworthy AI, and that's one of, let's say, if you want one of the takeaways I want you to have from this talk is, that if in the methods that we develop to think about trustworthiness. So here's, let's say, the barriers for power systems and why AI has not found as much of an application yet in power systems. Okay. It's coming, but it's not yet there. And the thing is that a lot of AI tools are considered a black box. So why would we trust a black box to run our system, right? When we test our methods, so we developed an AI tool, we test its performance before we deploy it. And what is the performance metric? It's usually statistical. It's accuracy, for example, right? So I get a bunch of data points, and I pass them through my AI tool, and I measure, okay, what error do I get? It's like 1% error, am I 98% accurate? Am I 99? Am I 95? And then assuming that this data are representative of my real situation when I deploy the neural network, then I tell my client, please go ahead, deploy it. You're going to be 98% of the time, you're going to be safe, right? So statistics, however, are not enough when you're talking about safety-critical operations. Statistics are good when you do forecasting, because then there's no better option. It's such a complex problem, so in forecasting, you actually need to have some tool, and then you can be as accurate. You can never be anyway 100% accurate. That's one, for example, option. At the same time, and then this is something that you will also listen if you have not already heard, I mean, you have spent decades developing models. Decades. It's millions of person-hours developing good models in order to simulate the power system and be able to predict or anticipate blackouts. So why would we do away with all these models and just go to something directly data-driven, right? And that's where it comes that then we're talking about trustworthy AI, and we're also talking about physics-informed neural networks, and also a number of people here have talked about physics-informed neural networks, and I'm happy to see that there is this interest, or let's say this kind of movement towards how to best take advantage of both the physics and the data, right? Because that's the goal at the end of the day. To take advantage of what we have to produce something better. Okay, so when you design an AI method, please consider interpretability. So how can I explain the decision that my AI tool takes or makes, right? You can also consider verifying your neural network if this is like for a control of a safety-critical application. You can consider physics-informed neural networks, and you can also consider, as we also see it in reinforcement learning now, also the winning algorithm of the RTE competition, learn to run a power network that is an RL algorithm. It is actually safe if you want by design. So it predicts or estimates an action, and then it projects that into the feasible space. So making sure that the constraints are not violated. So you can also add something like that. Okay. But think about how you can also ensure safety if your tool runs a risk of actually violating safety-critical constraints. Okay, so that's the first part. Now I'm going to spend a couple of slides on physics-informed neural networks. I'm not going to have any equations, but I'm going to have some motivation. Okay. Physics-informed neural networks can be used for many applications. What we are looking at is actually in the family of scientific computing. So how can I accelerate existing numerical tools by 10, 100, 1,000 times? Okay. I'm not talking of a delta improvement of, let's say, 50% faster, or even 2 times faster. For that, we can use our conventional tools, and maybe we can achieve something like that. if we really want to change mindset, change the type of tools we are using, we must aim at least 10 times faster, or I don't know, maybe that's my take. It can be 5 times faster, but something that's not an improvement of 10, 20%. Okay. Otherwise, also, the vendors will never accept something like that. Or the utilities, yeah. So why can neural networks, have you thought about that? Why can neural networks be faster than conventional methods? Let me go back. Have you thought about that? What do you think? What about the type of operations?
Models are typically numerical. You need some numerical methods, iterative, to arrive to something feasible. Neural networks, once they train this matrix multiplications, vector multiplications,
very good.
algebra.
Yes. That's exactly the. So, because most of our problems are nonlinear, and then we require numerical methods that are iterative, right? And what neural networks do is that once we train them, as you said exactly, then it's a matrix multiplication. And that's why it's very fast. Okay. So the idea is to replace, if you want, this kind of iterative numerical methods with something that's very fast in real time, but I have spent time training it, right? So in a way, I'm actually offsetting, or let's say, offsetting the time towards a period that maybe is not time critical in order to be much faster when I really need the tool. So, and then what's the benefit of physics-informed neural networks over the standard neural networks? Some of you might have thought about it, some may not. But the idea is that I include the physics inside the neural network training. So instead of actually minimizing a loss function, that is, let's say, minimize the error between data points, label data points versus what the estimate of a neural network is, I minimize the error between the output of the neural network and an equation. And if I do that, I don't need to generate databases. I don't need to generate data. I train the neural network just by fitting it into a model. That's more or less what I do. Okay? In order for this to work well, we have found that only the equations, it doesn't work so well. So we need a mix of data and equations to achieve a good performance. Okay? This data can also be generated by simulations if we don't have real data. Good. Now, the plan is, or what the goal, as I said, is to be 10 times, 100 times, 1,000 times faster, depending on the applications. Okay? And it's already finding quite some, let's say, traction in computational physics and computational fluid dynamics and others. So, in the next two slides, I'm going to present you an example, how I have applied physics-informed neural networks in power system dynamics. And then we're going into the graph neural networks. So 2-3 slides, yeah. So what we did here is we worked with Ørsted. Ørsted is the largest offshore wind developer in the world. And it's actually, its headquarters a few kilometers away from here. So what they do is they need to perform a lot of dynamic simulations to tune their controllers for the wind farms. So before actually they build, or let's say they deliver a wind farm, they need to perform a lot of simulations in the design phase to design their controllers to make sure that it does not create problems for the grid, right? So they are looking into how to accelerate this design phase. And then we work with them in actually replacing a wind farm model with a physics-informed neural network. And what we're trying to determine is the region of attraction. So imagine you have a controller, this is a phase-lock loop, you don't need to care about what exactly is this controller. So you have a controller, and I want to understand if I excite my system, so if I start from an let's say, an initial point that's not an equilibrium, if this is going to converge to a stable point, right? So how far can I go? The better the controller is, the further away I can go, and I can still converge back to a stable point, okay? So I'm checking that iteratively. So you can imagine how many simulations this is. So this is now results for a region of attraction for different set points of a controller for 250,000 points, right? And the only way we can check if this works or not is by inspection. So we have our conventional simulation or conventional simulator and our physics-informed neural network, and we can see that actually it works pretty well. So after that, we went to 5 million points. Okay, and we couldn't do that with our conventional simulator. It would have taken about 2 days in a high-performance computing cluster, and we were able to do that with these neural networks, 90 minutes for the training, 30 minutes for the evaluation. So it can be 25 to 100 times faster, and that's just, let's say, it's a proof of concept if you want. It requires a lot of work still from all of us to arrive at something that can be actually usable or deployed in large scale at the industry. An added benefit, if you want to think about it, is that once trained, a physics-informed neural network can run on a laptop. It's a matrix multiplication. Okay. But of course, the training is computationally intensive. Good. Now, we have trained, this is a single, let's say, wind farm connected to the grid. The grid is represented by one bus, so it's actually a small system. What do we do when we have larger systems? You have ideas? So our first idea was to take a neural network and simulate the whole system. And that didn't work very well. First of all, it doesn't scale very well. So we managed to go up to 57 buses, or maybe even a bit more. But it will not go to 1,000 buses. And every time the topology changes, and that's one of the main motivations also for the graph neural network we will discuss right after, is that every time the topology changes, the neural network has to be retrained. So that's not viable. So the idea we're working at the moment is what we call, in short for us, PinSim. And it's actually a modular way to create a new simulator. Okay. So what we do is we create a different neural network for every component. And now we're working on actually creating a solver that will bring these neural networks together and solve them together, right? So instead of having a library of conventional models, we can have a library of neural networks. If we have this solver, like, I don't know, how many of you have used Power Factory? I'm not so sure. Or any of these conventional solvers, we have now a different solution algorithm that brings interfaces all neural networks together and gets the trajectory out, the dynamic trajectory out. So this is a way to deal with problems like topology that cannot be learned by conventional neural networks. That's about dynamics, that's about physics-informed neural networks. What we're going to discuss now is again a little bit of physics-informed neural networks, is again about how we address topology, but for steady-state power flow. Okay. The idea is that I want to create a method with both of what I have said so far. So both the graph neural networks, but also the pins. I want to create methods for two reasons. First, I want to be much faster, so then I can actually generate, or let's say simulate a lot of scenarios in much shorter time. But then I can also create proxies. If I can have a reliable model, let's say, of my network that can capture topology, then I can put that in an optimization problem, and I can capture a -1, and -2, and -k. Okay, faster than all these nonlinear equations that I need to involve. Same with pins. So the previous case, for example, it captures differential equations. There is no efficient way to have differential equations inside an optimization problem, or a multi-period if you want optimization problem. So maybe pins can act as a proxy there. These are just ideas. We haven't tried that. But there is potential. Okay. So this is work with Agnes. Agnes used to be with us as a postdoc, and now she has moved to Imperial College. This is the first time I actually talk about this work. It's a preprint. You can find it also on that link if you want. Okay, so what is the goal? The goal is to train a graph neural network to estimate voltages and line flows of n minus k contingencies. Okay? And there are papers about this. Our goal with this work is, first of all, use the GNN not necessarily as the most accurate estimator, but rather as a screening tool. What I want to do, I want to screen millions or billions of scenarios, pick the most critical ones, or find what are the most critical ones, and then run normal power flows or whatever I need to run on those. Okay. So I need a very fast screening tool. That's number one. Number two is, because there are also works like this, I don't want to train on n minus 2, n minus 3, n minus k. I want to train only on the base case and n minus 1. And then the graph neural network should infer the rest. So I want to see how possible it is to train only on a limited set of contingencies that is actually tractable. N minus 1 is tractable. That's why you also have still n minus 1 security criterion. And then let the graph neural network infer what happens in n minus 3. Okay, that's the goal. And why GNN? Exactly because it captures topology. So let me give you an example. So these are now the 4 systems that we have used for this work. 6 bus, 24 bus, 57 bus, 118 bus. The 118 bus, I guess some of you have already worked with that, has 178 lines. How many n minus 1 contingencies? 178 in terms of at least lines. Let's focus only on lines here, okay? Or branches. How much n minus 3 contingencies? Almost 800,000. Okay, it grows exponentially. Now, 800,000 contingencies for a single demand and generation scenario. Now, over a year, we don't have a single demand generation scenario. Of course, we have some critical ones. And then I just may make a thought exercise. It's not necessary that this should be like that. But let's suppose that I have 19 generators. And I just assume a high and a low generating scenario for each of those, right? How many combinations do I have? 2 to the 19. And then what I say is, again, that's out of my head, right? I assume that's a single load profile. I assume that the load over the day may be very uniform in that region of the world, in that grid. So let's assume that I have only a high and a low demand scenario. And if I combine that, then I have 2 to the 20. 2 to the 20 is 1 million scenarios, generation demand scenarios. Times 700 or 800,000 contingencies, we're talking about 700 billion scenarios. Okay. So I need, normally, if I want to check for everything, and let's assume we want to do that, I need to check for 700 billion n minus 3 contingencies. Okay. With AC power flow. And the question we ask is, can graph neural networks do that faster? Okay. That's the whole point. By training only on the n minus 1. This doesn't work so well. By training only on the n minus 1. So can they infer what happens in the rest? Good. Any questions so far? Because that's how we set the problem. Is that clear? You have a question? Yeah. You have to unmute, sorry. I forgot that.
Okay, no? My question is why we need to secure against contingency n minus 3? Because if we screen the system for n minus 1 and it's secure, we don't need to consider n minus 3. The probability of happening n minus 3 is completely negligible. Even n minus 1 doesn't happen a lot.
I agree that the probability of n minus 3 is much lower than n minus 2. However, if you see the blackout that we have is actually, because we have already secured the system for n minus 1, the blackouts that appear are because they are going beyond n minus 1, n minus 2, n minus 3. Having a more complex system, it's more probable that maybe 2 components fail. So there is actually a trend to actually consider maybe more contingencies. And the way to do that is also probabilistic. Maybe you don't need to consider all n minus 1, all n minus 2, all n minus 3. You can think about risk. This is another way to do that. But then you need to consider some higher risk n minus 2 and higher risk n minus 3. Okay. Very good. Oop. So what I'm going to do here, we work with 4 different neural networks, right? 2 of them were the guided dropout, based on the guided dropout, and I'm going to briefly explain what guided dropout is. And the other 2 were based on this edge-varying graph neural network, okay? And now, for each of these families, and I'm going also to have a slide about that, for each of those families, we explored if physics or physics informed helps or not in a better inference of the neural networks. So I'm going to present them 4 different models. I'm going to compare them. And then I'm going to compare their performance with DC power flow. Because this is, let's say, when you go beyond n minus 1 and you consider, let's say, cascading outages, this is what you are going to use, DC power flow, because it's more computationally feasible. And then I'm also going to assess their performance in terms of time. Okay? So 3 things. Let's talk about guided dropout. This is actually an idea that came by Benjamin Tonneau and others of how to encode topology, Partial topology, into a neural network. Okay. So what did they do? They took a neural network. In the input, they have the bus power injection. And then they have a bunch of neurons, but then they have some conditional neurons that are always off. But if a line is out, then I turn this neuron on, right? So I activate the neuron. So by learning the base case and what happens if I take a line out, then I actually have maybe 1 or 2 or more neurons. For us, it works with 2 actually. So 2 neurons per line outage, if you want, or per line switch in and out. This can encode how the flows change. Okay, so base case, no neuron in. I take a line out, and then the first neuron is here activated, and then I learn. So the weights here that are learned with this topology. So this actually neuron here captures the change, the topology, the change in the flows. Okay, that's an example with 1. As I said, we have used 2. Here, then another line is out. Then I learn the change topology or the change flows based on this topology through this change in my neural network. Okay. So I adapt my neural network or the topology of my neural network to capture the different topologies in the power system. It's actually, to be honest, a smart idea, and it has shown to actually that the principle of superposition kind of works. So the idea is that then I can have both neurons out or both neurons in, and I can capture the topology of n minus 2. So 2 lines out. Okay. So what do we do here? We train for this. So the base case, and then we train the weights with a single line out every time. So we train for n minus 1, but then I test for n minus 2 and n minus 3. So my testing set has actually all the this kind of combinations of neurons, and see how that works. Okay. That's the guided dropout. Questions? Good. Now, a slide about the graph neural networks. So this works a bit different because now the neurons are connected in the same way that the topology of the grid is, right? So we have weights where we have also branches, if you want. Now, the cool thing is actually how you capture the dependency between the different nodes. And then you can have several layers. So this is what we call here hops. So here in this first case, this captures, let's say, the change in this, if you want, whatever, voltage will be dependent only on the neighboring buses. So that's the first hop, right? But then you might realize that, you know what, no, I'm also dependent on two buses away. So maybe I need to capture also 2 buses away, or maybe 3 buses away, right? So it gets quite complicated, but the graph neural network can theoretically capture interdependencies between nodes or across nodes that are a bit further away. Okay. It's a designed criterion how far you want to go. Questions with that? Okay. But then if I capture the graph, right, of the topology of my system in a graph neural network, then I know if I have a line out, I know which actually edge I have to deactivate. Is that clear? It's more straightforward, I think, than the guide dropout in that sense. Good. Now, and besides these 2 families, we also considered adding or not adding the physics. So besides actually training on data, we also added the power flow equations here. So an additional loss term, where we also try to minimize the deviation of the neural network output from the power flow equations. So we also test for that. Okay. So in here now are the first results. So we have the first we compare if physics make a difference. Yeah. Is it maybe you need to unmute? Yeah.
Yes. Yes, a question on the previous slide. When you say that you insert the power flow equations, which power flow equations? Does it need to be linear? Can it be the AC?
We have the AC power flow equations, so the exact ones.
Okay.
They can also be, we have not tried the linear ones, but we want to be as exact as possible, so to have this loss as close to the, I don't know if you want to call it reality, but as close to that model as possible. So it's the non-linear ones.
Okay, thank you.
It could be interesting to see if the linear ones could also do an equally, yeah, how they perform. Yeah. Okay, so these are results now. What you see here, it's a bit busy, but I'm going to guide you through it. So this column here is guided dropout, this family, with and without pins, without a physics-informed term, and this is graph neural network, okay? And what I want you maybe to focus is on the mean. So what we plot here is the mean absolute voltage error. So this is the mean error of the voltage, the bus voltage at the output of the neural network in per unit, right? There are different axis limits here just in order to improve the visualization. But what I want you to focus is on the mean absolute error for the voltage, for the bus voltage in every case. And you can see that it's quite consistent that in the graph neural networks, the physics-informed graph neural network performs better than without the physics. But in the guided dropout, the one without the physics performs better, so a lower error, than the one with the physics. Okay. Why? We are not sure yet. It's up for exploration, right? But what we did after that is that then we focused only on 2 of the 4. So we focused only on the guided dropout without physics and on the graph neural network with physics. Okay. So the rest of the results will focus only on these 2 in order to make it also a bit easier to compare. Clear so far? Good. Now, the next analysis we did is on regression. So we use a neural network to estimate numerical values. We estimate the output in terms of bus voltages, but also line flows, right? So I'm only going to present here the line flows. The voltage results are actually better, but I prefer this because then I can also connect that with a DC power flow that I want. Okay. So here are the results for the n-1. So remember that we trained on n-0, n-1, so this is really what has been trained for. And you can see that, for example, for the small system, this works actually, sorry, I haven't explained what you're seeing, right? So guide dropout and graph neural networks, first of all, the 2 columns that we compare. And what I have here is the actual line flow or line loading in per unit. So this should go from 0 to 1, the line loading. And then this is the predicted one. Okay, so maybe not, it's in per unit. The line loading per unit does not go from 0 to 1 necessarily. And this is the predicted one. So the good performance is if you are exactly on the x equals y line. Okay, so then it's 1 to 1. The predicted is equal to the actual. That's what I want. I want actually a performance like this one. This is perfect. This is also good enough. Okay. You can see that the graph neural networks perform a little better, right? So they do perform a little bit better. But it's okay. I mean, they could also get better than that. Yeah. Now, let's go to the interesting stuff, though. N-2, N-3. Okay. And this is now the results on N-2 and N-3. I haven't tested. I haven't trained for that. So obviously, the performance is getting worse than what I have trained for. But something like that. So for the fit same bus, this is actually a pretty good inference, right? As I said, what I want this model for is to screen. So I want to screen millions or billions of scenarios and then just keep the most relevant ones to analyze them further. Okay. So this is the performance we get. Is there improvement potential? Absolutely. How? Maybe it's up to you. I don't know. We need to. It's an open topic. Yeah. There's a lot of things one can adjust, change, optimize to improve that. Okay. Yes.
One thing that I noticed is that, the 57 bus performance is better than the 24 bus actually for all of the. And do you know why? Why is that happening?
It's the characteristics of the network. I cannot tell exactly why, but it's the probably the topology or the.
Okay.
Yeah.
Okay.
Yeah, maybe this also reminds me of one more point because we actually tested that over up to 500,000 points, but this test data points that we picked randomly, right? So if we pick different test database, maybe we'll see different things. So this is also something that one has to keep in mind. You have a question? Yeah. Yeah.
I'm just curious if because you are using these to identify certain N-3 cases, for instance, right? But did you identify like false positive and false negative alarm? Did you investigate that? I'm curious too.
Yeah, that's my next slide. Okay. Other questions? Great. So since Licio asked what we did with false positive and false negative, so exactly this is the question we asked. Since we're doing screening, maybe we're more interested not in the actual numerical values, but how often we can identify critical contingencies, or let's say line overloadings. And that's why now I saw this and not the voltage, because I want to compare that to the DC power flow. So indeed, that's what we did. So here is again for the N-1. Here I do classification. Okay. Again, the same columns. We have no, it's different. Sorry. So we have the two different classes. If a line is congested, so there's like say a violation, we go beyond the limit, or if it's a normal operation. Okay. The metric I use is called recall. I think some of you are familiar with recall. It's the so-called true positive rate. What it measures is how many true positives I have out of the total positives in the class. So out of the total class that I have here that is, let's say, normal operation or uncongested lines, how many of them was my network able to determine? A good value is 100%. A really bad value is 0. Okay? Yeah. Obviously, if the class is small, right, if I don't have so many congestions or line limit violations, then it's more challenging for my neural network or any tool to determine these violations, right? So the best for these classification problems is to have balanced classes. That's when it works best. Good. So what do we see here? That's n minus 1. Again, we have trained for that. We see, obviously, the uncongested case is quite large, or the class. So and we see actually that probably, so this is DC power flow. The green is DC power flow. This is guided dropout, the blue. And the orange one is the graph neural network, right? And we compare, our ground truth is the AC power flow. That's why you don't see it here. So the AC power flow is the true values, and here is the comparison between the three. And you can see that, I would say that they do a pretty decent job, most of them, but for the violations, they do a pretty lousy job. Okay. DC power flow included. To be honest, the graph neural networks and the guide dropout are better than the DC power flow. That is actually the benchmark that's also used, I think, or has been used extensively. Okay. Now let's go and see the n-2, n-3 only. I just keep n-2 for, I don't know, time efficiency, if you want. I mean, all these results are in this manuscript if you want to go and get a better look. Also for voltage, not just for line flows. So here is n-3. Again, we haven't tested for that. What we see is, again, pretty okay for the base case, but what is interesting for us is the violations. And then DC power flow is really at 0. So they don't really, it's not able to get the critical line flows. And then there are different performances in different systems for the guide dropout and the graph neural network, but they still, for the larger systems, they're about 35%, right? Which is so-and-so. So why do you think, or how would you improve the performance? Now somebody comes to you with this problem. What do you do? You can just come up with anything, right? Make what bigger? So the one option is to make it bigger. Make what bigger? The network. Yeah. True. Make it bigger. Yeah. Training data. Yeah. Very good. So what about the training data?
Then you try with more cases and different flows.
So more cases, different flows. Yes. That's an option. Yeah. Others? If you use a real network, talk to RTE, yes. Oh, if it's from France, yes.
They need to solve this problem.
Yes.
The operators are actually doing this and they know certain things about it.
Yes. Mm-hmm. Very good. So all these are good ideas. What we think needs improvement is data. Of course, all the others can also, I mean, probably also a bigger network or a different, I don't know, some other physics. But what we think is database is important. We need to have balanced classes. And it's a huge search space. Right? If you think about the number of scenarios, even for the 178 n-1 times a million, we're talking about 178 million possibilities, right? So how do you actually pick this kind of, I don't know, 50 or 100,000 data points that can help you? Or 500 that we have it's here. So 500,000. So that's why we think that data is important, and this is an open research topic as well. We need, if we want to do good AI, then we need to actually have good data. Real data is one option, but real data is not always available. So creating databases or finding efficient ways to generate efficiently databases with information-rich content is a challenge in its own. Scientific challenge, right? So we have tried to do some things, and this is just a plug here if you want. We just came up, Bastien is also here in the room. He has an open source toolbox that you're welcome to use. It also does n-k, n-1, sorry. And small signal stability. Good. Now, let's go to the original question. So which method do you think is the fastest? So the options are the following. We have DC power flow, we have AC power flow, we have the guided dropout method, and the physics-informed graph neural network. DC power flow. Very good. So we have 1 vote for DC power flow. I'm finishing in 5 minutes. Okay. That I left it open on purpose, right? So let's see how it's only execution, and then I have also the results with the training, right? So these are the results for the 4 different test systems, just for execution. So I have already trained, and I only evaluate. Okay. This is logarithmic axis. What does this mean? This means that the bar here, so the lower part of this bar is not it's not proportional to this one, right? Here is a lot more time condensed than here. Good. So then the neural network methods can actually be 100 to 400 times faster when we only talk about execution. 100 to 400 times faster means that if I want to run 100,000 scenarios, I can run them in 1.5 minutes with a neural network, but I need 5 hours with AC power flow. Okay. So it's big. And now imagine if you want to do millions. Right? So the speed is there. Of course, we need to improve the performance. And also, if this is, let's say, faster, then you can also plug it in an optimization problem and then maybe improve the performance there in terms of time or convergence. Okay. So this works well. There is no real difference between guided dropout and graph neural network. You can see that they are more or less similar. What was also interesting for us is we didn't see a big difference between DC power flow and AC. So our hypothesis there is that AC, or the solution methods for this kind of quadratic problems, has improved so much that we don't see at least a difference in our tests. Yeah. Now, what we've included training time, right? And this is my last result. So this is what how things. It's a busy slide. I will guide you through it. Again, for different systems, again the same cases here. We have DC power flow, AC power flow, guide dropout, and the graph neural network. DC, AC, guide dropout, graph. That's one. Yeah. So let's focus on this first. So you can see that then. Okay. And what I plot in these 2 bars, that is for the neural networks, is how much time it took me the dataset generation, because this is also part of the training, the dataset generation, and the training, and the execution. Okay. So I have dataset generation, training, and testing. That's what I have. So you can see that, let's say, for the 24 bars, dataset generation, training, and testing is already 10 times faster than running DC and AC power flow. So that's good, actually. But for larger systems, we see that the trade-off, at least in this test, is about 500,000 points. So if I want to go over 500,000 scenarios, then it might make sense to go into a neural network solution. There's an asterisk or a footnote, assuming that I am satisfied with the performance. Right? And I can tell you that probably you will be satisfied with the performance against the DC power flow, but the real benchmark is the AC power flow. Okay? Good. Now, an interesting maybe comparison as a last point is the difference between guided dropout and graph neural networks, because this is physics informed, so I need less data, and this is only based on data. So what happens here, and it's interesting to see, I guess some of you might have seen that already. In the guide dropout that's only data-based, I spend more time generating my database, I need more data, but then my training time is faster. But in the physics-informed, I need less data, so less time in generating data. Again, this is logarithmic, so this is not the same as here, right? So it's exponentially more. But then the training is exponentially more. So there's a trade-off there that one has to consider. Good. Last slide, conclusions. Yeah, first of all, if we do AI applications for power systems. As long as this is safety critical, then we need to be somehow trustworthy. So I hope that you will remember that. And then we talked about graph-aware neural networks, so guided dropout and graph neural networks. What we try to do is we try to find ways to accelerate a huge, so a problem that's actually exponential, how to do n-2, n-3. And we found that it can be 100 to 400 times faster, but of course, we also need to look into the performance and how to improve that. Okay. Any questions? Yes, Nick, let me just.
Did you also try to include maybe just a few n-1 cases into the training and to see how much better it would get? Just like with small number of them.
We have all the n-1. You mean n-2? Or
oh, sorry, n-2, if you included a couple of them.
We wanted to avoid that by design, because the moment I open the door to n-2, then I don't know where to stop. But I want to create a tool that can infer from n-1 the rest of the topologies. So that's why
maybe just like, I don't know, 0.1% of possible combinations would already increase.
Could be. Yes, this could be something. I find it an equally, at least from a research point of view, interesting challenge to have no n-2 and see what you can do with all the data that on the n-0 and n-1. So how more can we improve this? But yes, it's definitely a point you can. Yeah.
Thank you very much for the great presentation. So, in a way, this is exactly the information I was looking for from the summer school. So 2-3 months ago at AirGrid, we started to exactly try to solve this problem, because the DC and AC power flow could take weeks to run for each hour for 50 contingencies for the whole year. So we actually work for the long-term planning, and may I ask what happens, or how do I solve, or how do I think about when I have to add a node or multiple nodes or lines to my, let's say, model? How do you think we should be thinking about that?
It's a cool question that I haven't thought about, to be honest. That's a very nice question. So first, I will start by saying I don't know, but I can start, let's say, thinking about that. And here are some pointers. I think then what one should do is add one more neuron, right? So I need to add a line. So I add one more neuron. The thing is, and that's the challenge that it needs to be solved, is that if you add a line, then you know more or less the reactance of the line. So you know maybe the length, or you know the characteristics of the line, right? And you don't know that from the weights. Okay, so here's what I would do. I would go to the full-blown system, so what the maximum of number of lines that you can add, and I'll create that system, and I will train on that with n-1. So taking a line out. So, and then work backwards to the system I am now, and that's how you can optimize and see which lines makes most sense to add. Does it make sense? Yeah, it does. Yes. Yeah. Yeah.
Thank you very much. Do I understand that given the number of bosses you have, when you are creating the neural network, you have to create the number of neurons to be equivalent to the number of bosses you have?
Correct. What I didn't discuss is that there's also a layer in the front and at the end that's fully connected layers. So there's more neurons than just the nodes. Okay. But indeed, you did need at least as many neurons as the nodes.
Really? Yeah. Okay. So, again, it's similar to the question I asked, I forgot her name, the professor from yesterday, about applying optimization to AC power flow. And the question about given the more the bosses you have and the more contingency you go to m-k, the combination explodes, yeah? Mm-hmm. And the question is, have you considered the model reduction to kind of like, of course, try to scale down the system to smaller nodes or smaller bosses that have equivalent representation of the bigger, assuming that you have 1,000 nodes, and then you are trying to reduce these nodes to, say, 50 nodes that should give equivalent electrical characteristics. And this gives you fewer combination of n-1, that in theory could simulate similar consequences. Yeah, and I'm wondering if you think about exploring these, such that in this scenario of reduced node combination, you could potentially run n-2, train your model in n-2 or your graph neural network in n-2, but with less combination.
Got it. Yeah. True. Actually, that's a very valid approach, especially with conventional methods. That's exactly what people try to do, and focus only on the lines that are relevant, right? So interconnections maybe that are important. Yeah. Our goal here is actually to replace this computationally intensive method with a graph neural network that is 100 or 400 times faster, but keeping the full detail. So that's the first step. If we manage that, then of course, one could actually create an equivalent with a reduced order model. But it's the same exercise as what we do here. For me, it's more interesting to keep as much of the detail as possible, but make it orders of magnitude faster. Yeah. There is first.
Thanks. I was just wondering whether it kind of makes sense to use the neural network as a warm start for then making like subsequent AC load flow.
You could. It's interesting to see actually how much. Indeed, it's interesting to see how much you can save in computation time. Yes. What I would also add to that is maybe you can include the neural network to an optimization and use that as a first way to see which, what is the solution of the optimization with that, and then try to check for different scenarios. So use the optimizer to search maybe best topologies or worst case topologies based on the graph neural network, and then simulate them and see what is the worst case really. Does it make sense? In the AC power flow, I think that's a good point. It's good to explore that. I don't know.
Thank you very much. I was also super surprised and impressed to see that it's actually better than DC power flow, but also that the performance depends a bit on the topology, as you mentioned, on the characteristics, whether it's more radial or more meshed, the network. And I was wondering if there's a simple way to improve the performance by differentiating the characteristics of the network. For example, I don't know, for example, using the weighted degree of the network to see before if the network is super meshed or super radial, and then instead of a one size or one model fits all solution, have like for this degree distribution, take this trained network, for this degree distribution, take this, and then you have maybe a much better performance already.
Yeah, that's a great point. I completely agree. So it's how meshed the network is. And that I think what actually this can inform is the number of hops in the graph neural network, right? So how much dependent am I in the, if I go back, you can see that here. Yeah, here. So here it's, the more meshed I am, the more interdependent I am across nodes, right? So I can take the degree and then maybe here have taken, I think, 2 or 3 hops for all networks. Maybe you can differentiate across networks based on how meshed they are, right? That's a very good point, yeah. I agree.
Yes. As you told in the beginning, the solving time is one of the most important things to make the vendors trust such methods. So the question is that if some small topological change happen in the network, if it is possible to avoid retraining and with some technique make it possible to solve such analysis without need to retrain.
Yes, but this is exactly what this captures, right? The topological changes. So you don't need to retrain. Because of?
Color representation.
Because of the graph neural network or the guide dropout. But it's exactly, so you don't retrain, you train once, and then it captures all the topology. So that's exactly what we're trying to capture. Yeah. Last one? Yeah.
As I understood your network.
You have to...
As I understood, your network outputs like the flows or voltages or whatsoever, but your main goal is only to say if this can be potentially dangerous configuration or not, and to try solve it then with AC power flow.
Yes.
Why not then to train just that your whole network outputs a single probability value? How risky this is to tag this actually, so it would be much easier for the network.
True. That's a different metric. Indeed, we haven't used that output. Indeed. That could be also a good way to go for that. Yeah. I mean, the way we started is first we wanted to be as exact as possible, and then we actually saw, okay, if we're not as exact as we can, then what can we do? If we can classify better or things like that. But this may be a more tailored metric. That can
because
work.
since anyway you will still validate it
Yeah,
with a proper power flow.
Yeah, that's very good. Yeah, thanks. Okay, so I think for the sake of your break, we'll stop here. Thank you very much, everybody.